Good evening, everyone. In this video, we'll be talking about relations of class and state models. So the state model actually specifies allowable sequence of changes to objects from the class model. This we have been discussing. Okay. So basically, the state models, you will have several states. Okay. So these are allowable sequence of. Okay. So the transitions are allowable sequences of changes. Okay, to objects. Okay, and the objects are per class model. Okay, so from the class model, you have the class, and for each class, you will have several objects. Okay, and the objects will be in several states. Okay, and the state model basically shows this sort of allowable sequence of changes. So what are the transitions that can actually happen that actually makes them move across these different states. Okay, that we have already discussed. A state diagram describes all or part of the behavior of the objects of a given class. Okay, so the objects whatever we are discussing about, the state diagram describes either all the behavior of that objects or part of it. Okay, some of the things you may ignore because which may not be so important. Okay, we have been discussing it is all about abstraction. Okay, to what level you want to put the details. In that sense, okay, the way we have actually discussed, states are equivalent classes of values and links of an object. So how these objects, okay, will be in different states. So in that sense, state structure is actually related to and at the same time is constrained by the class structure. So they are more or less directly dependent, okay, on one after the other. Okay, so you have the class structure, you have different classes will have different objects, and different objects, the objects will be in different states. That's how the state structure is related, okay, to the class structure. Okay. That's about the class and the state models at the model level is concerned. Okay. So of course, we have been discussing, a single object can have different states over time. Okay. So the states, okay, so a single object can have different states, and these states are basically happening, okay, with these sort of events. So across the time, it will have several states. Okay, that's how the state diagram and the state model actually shows how these objects are changing across these states. Okay, so in that sense, inherent differences among the objects are actually properly modeled as different classes. So if there are two different classes are there, okay, so if their objects are completely different, okay, these differences are inherent. Okay, so you can actually see them, the differences will be in their structures, in their attributes, everywhere it will be different. So objects will also maintain their identity, so that means that's how they are into the classes. So if there are two different classes are there, they are inherently different, the objects from those classes are. Okay, so that's how inherent differences among the objects are properly modeled as different classes. But then temporal differences are actually properly modeled as different states. Remember this one, of the same class. From the same class you have several objects, and these objects over time have certain differences. And this is what is actually represented by the state law. Okay, so and these are actually shown as states. Okay, hope that is clear between these objects and the states are concerned. We already have discussed a composite state is an aggregation of more than one concurrent substate. Okay, this we have discussed in detail in one of the videos. Okay, so a composite state is an aggregation of more than one concurrent state, and there are three sources of concurrency. These things also we have discussed them in detail within the class model. Okay, so there are three sources of concurrency within the class model. The first one is about the aggregation of objects. So each part of the aggregation has its own independent state. We have discussed about the car and its ignition and all these things, so the brakes, accelerator, and everything. Okay. So each part of the aggregation has its own independent state. So at any particular time, the assembly is considered to have a state that is the combination of the states of all its parts. We have discussed this very in detail when we were discussing the example. So the class and those respective parts, which are aggregated at the class level. Okay, and so the assembly's state is actually a combination of the states of all its parts. Okay, That's about aggregation of the objects, and then like say for example, that's where the concurrency is, because like the see, each and every part is basically having its own state and its own state diagram. That means like across time, like they are moving across the states. Sometimes they are independent, sometimes they are restricted by other things, but then like that's the concurrency level we have actually achieved. Okay, for this sort of assembly state is concerned. So the second level of concurrency we have seen is aggregation within an object. So this also like we have discussed. Okay, so the partition the object into subsets of attributes and links, and each of these subsets will have their own subdiagrams. Okay, and then like the state, okay, the composite state of a particular object at any time is basically a combination of these two states. Okay, across these subdiagrams, and we have seen them in detail. The third source of concurrency within this sort of class model, we have actually seen at this sort of behavior of the object itself, concurrent behavior of the object itself. This we have seen with the example like an object of, say for example, which is returning, say for example, that returning the cache. It has to return both the cache and it also has to return the card. Okay, so that's a concurrent behavior of that particular object. Both these things have to basically go on concurrently. Okay. We also have seen like to finish that particular state, to complete that particular state, you have to finish both these parallel behaviors, so the concurrent behaviors of that particular object. Okay. So that's how like the concurrency within a class is actually modeled for the state diagram. Okay. We have seen all the three types of concurrencies possible. Okay, more or less related to this sort of composite state. Okay, so it will be the aggregation of these subsets. Then another interesting concept is we have seen like say for example the generalization relationship among the classes. We have the subclasses and superclasses. What happens to the state models? The state model of a class is actually inherited by its subclasses. Okay. But the interesting thing comes is like when the subclasses can also have their own state diagrams. So the superclass has its own state diagram, which is inherited by the subclasses, but the subclasses can have their own state diagrams. The case appears because of the two situations. And then like say for example, if there are two different class diagrams, there's two different state diagrams, the subclass and superclass, how do they actually interact? So the superclass has its own state diagram and the subclass has its own state diagram. So you put both these things in one state model. How do these state diagrams actually interact? That's again an interesting thing. So we have been seeing like how different state diagrams are actually interacting among themselves. They even have conditions. They have restrictions with other state diagrams. Here comes two cases. Okay, so with this sort of subclasses and superclasses. If both these state diagrams of the subclass and superclass actually deal with destroying sets of attributes. So the superclass has certain attributes, okay, and the subclass has some more attributes, but then like it is actually inheriting this superclass. Okay, so that means like it is inheriting those attributes as well. And if we have two state diagrams for both the subclasses and superclasses, then it is very simple, relatively straightforward. The subclass basically has this sort of composite state. Okay, so it will have the composite state. Okay, that means like it will have the concurrent, the concurrent state diagram for this sort of superclass. Okay, and its own attributes. So that means like we have seen this in the concurrency level. Okay, so the subclass has the composite state of composite state which is composed of concurrent state diagrams of both this superclass and also the additional attributes. So this is relatively straightforward. But what happens? We have seen like inheritance, and like we have even seen like overriding and all the things. Okay? So that means like you take the attributes of the superclass and you basically modify them. Okay, and then like you basically work with them. So if the state diagram of the subclass actually involves some of the attributes which are actually used by the superclass as well, then basically conflict occurs. This is a little bit tricky. Then the state diagram of the subclass, okay, superclass is there, subclass. So the state diagram should generally be inherited, okay, by the subclass. But if such conflict is occurring, so that means like you have the same attributes, here also like you are changing the same attributes. Okay, so in its case, the conflict has occurred. The best solution in this case is like the state diagram of the subclass is a complete refinement of the state diagram of the subclass. Okay. See, again, it's all about the abstraction. To what level like you want to really define all the things, okay? So that like it will make your uh, life simpler with this sort of object-oriented design and also like implementation of the states, all the respective, respective steps. Okay? So that's about these sort of subclasses and superclasses and their respective state marks. Then we also have seen the signals. Okay, signal hierarchy is independent of the class hierarchy. Okay, for the classes exchanging the signals. Okay, so they are more or less independent. Signal can be defined across different classes of objects. Okay, so see them like they are completely different. Okay. Signals are more fundamental than states, and they are more parallel to these sort of classes. That's why like we have even seen the generalization hierarchy of signals as well. But generally, you take like signals and classes are independent. Okay? I mean, the hierarchies are independent. So with this one, like we finished chapter 6 of object-oriented modeling and design with your Michael Blaha and James Silva. Thank you very much for your attention.